Alright, so the first component that we're going to work on is the screw terminal board. And the screw terminal board is available in kits for about $1 or so on eBay. You can, in fact, buy them pre-assembled. And they look like that. I usually get the Deke Robot ones, but the problem with them is that half the time the eBay listing shows you a picture of this and sends you the disassembled kit. But it doesn't really matter. It only takes a few minutes to do the soldering. It's not quite as clean. Obviously these guys are done on machines, but it also gives you a chance to get some soldering practice, and it doesn't take long to assemble these little screw terminal components.
Do you ever find that when you do get the pre-assembled ones that you have to modify them in any way? Is there any difference in the outcome?
No, there's no difference in the outcome. I mean, again, it depends on how good you are at soldering. But as long as you take the time to align these little grooves when you're assembling the bits, it doesn't add that much. Oh, look at this. So this kit has a flaw in it. What do you know? So here I am saying that it's fine, it doesn't affect anything, and as I open this bag, this one, for some reason, had a 2-terminal part, which is wrong. This is a little trickier than I thought it was going to be. So, in fact, this kit is incorrect. We're going to be missing a terminal because this kit had a flaw in it. Let me just grab another one here. You know, if you order stuff on eBay, always order half a dozen because of that sort of problem exactly.
If you need 2, order 3.
Yeah, that's always the case though with these cheap suppliers from eBay. Okay, so here's the next one. And again, it's easy to get these reversed, so be careful that you have the shiny sides on the same side.
Do you need to test them to make sure they're actually locked in place? Like, do you wobble them side to side?
No, you can usually kind of just look at them. And if you get them at a weird angle, like if one of those grooves doesn't go into place, when you try and put it on the board itself, it will not align very well. And the other thing that you have to watch out for as a beginner is you don't want to do that, because then it doesn't work. You need to have the wire entrances on the right side. They have to be on the outside.
Accessible to put the wires in.
Yeah. So I start with the outer terminals. And we can once you've got them together and there's no misalignments, there's no grooves, you just set it down and we solder a bit. Bring in my iron, and I don't put flux on these because, quite frankly, it takes so much heat and so much solder to attach these that there's lots of flux inside. The rosin core already has enough flux to do this job. You need to apply a little bit of heat because there's a lot of metal on the other side. This is kind of an unusual thing to solder. It takes a lot more heat than usual. Okay, and so you do one corner. And you just wait until the smoke disappears. I mean, you don't want to melt the screw terminals on the other side, but because of all that metal, it actually takes a while.
Well, you also want to make sure that the solder is nice and liquid and is flowing and making good contact with that post down through the board a little bit.
Yeah, see, it won't flow unless you give it some contact time to heat up. Otherwise, you get a cold joint. It'll look like a proper solder joint, but in fact...
So approximately 5 seconds of preheating, given the size of the amount of metal involved here.
That kind of depends on how big your iron tip is. We're operating at, what, 750 there?
Yeah.
So that's pretty hot. I usually run my iron around 650, but for these long strings, so I've done 2 opposite diagonal corners there, and this is just to affix it in place, and I'll do the opposite diagonal corners as well. And I'll press down on it once that's in. So I'm holding it till the smoke sort of dissipates there. That tells me the flux is burned off. Because these are the really thick ones, I'll give it a little bit more time. And if you just lift your iron up, you get that nice Hershey's Kiss effect on your solder.
With the thin diameter solder, you're also going through more than 1 centimeter, almost 2 centimeters worth of solder to make this joint.
Yeah, I usually work with 0.5 or 0.6 millimeter solder. So you know, these little rolls don't cost much. I think they're $3 on eBay, and you go through them pretty quick. But they're just the right size for your hand. You know what I mean? It just works with this kind of job.
Well, there's a don't burn your fingers caveat, which is, you know, be ready to put 1.5 centimeters of solder into the joint.
Yeah.
And so you have to have that much solder out, otherwise your fingers are going to touch the soldering iron.
Yeah. So there's my little anchors. Okay, so it's the 4 corners have been anchored. Before I go any farther, I just do a little visual check and make sure there's nothing that I have to undo. Uh-oh, look at that. See what I did there? I actually held that too long, and the plastic started to melt. So I made the mistake I was warning everyone about. That's probably still fine, and we can just do a little test with the screwdriver here. And if the screwdriver does not work, then we've mucked it up.
Oh.
So that's nearly a catastrophic error right there. Probably because I'm flapping my gums here. But that's what you want to watch out for. You don't want to hold the iron so long that you actually do what I just did. That does not look terminal. Sorry, bit of a pun there. Yeah, pun intended.
Actually,
it does look terminal. Let's zoom in on that, because I want to show someone. That was a cold joint, and I made an error, but it's better to show people the mistakes than the actual perfect one. So if I put my screw in there and I turn, it should focus in a sec there. I don't know if you can see, that joint is now a cold joint. It did not join.
You can see it rotating, and you can especially see here in this part here how that is wobbling, and so it's now detached inside its plastic casing.
Yeah, so this solder joint here is now a flaw. It's not working. So what I'm going to do is just quickly unattach that one, pop it off, replace that one segment, and then we'll start over again. So just take me a moment to do that, hopefully. Who knows? It's always interesting when you make a mistake in a demo, but sometimes it's actually better. So I'm just quickly pulling that out.
So you melt the solder and then physically pull.
Yeah, and because we checked this while we still only had the corners in place, it's actually not that bad to do. Okay, I'm gonna have to pull from this side.
So you're pushing against the board with your fingers to get it to come out. All
so
right.
I didn't plan on doing an error, but hey, we did it, so let's just go with it.
So what happens if the solder occludes the hole, like fills in the hole that you now need to put the pins in?
Yeah, the nicest way to pull solder out of a hole is with another piece of wire, actually. So we're going to have to do that here, but first I'm just going to find my melted section and pull it off. Okay, so there's the one we monkeyed up, and I'll put these back together. I think this one's still fine, doesn't have any melt on the plastic. And alright, let me grab another one from that other kit. And then we'll pull that solder out of the hole. Again, mostly it's just the awkwardness of working here with a video. And okay, so we have this issue of how do we pull the solder out. So generally what I do is I grab another, just a length of wire. This is just 22 AWG. It's actually the wire we'll be using later. I'll give it a bit of a spin, and I'll put some flux on that. And I will heat it up where we have this plugged hole, with the idea that the solder should flow onto the wire itself. And you could use a solder wick for this, but I find that often I don't have the wick handy, and especially for pulling solder out of holes, it doesn't quite work as well. And the other thing that you can sometimes do if you have a really big glob is you can heat it up and then just give it a sharp tap before it melts. Aha! So that worked. Let me zoom in on that, Trish. So that was just a sharp tap. Okay. And it was enough to just knock the solder out of the hole. So let's take a look at the other one. The other one's a little dirty too. I'm going to try that sharp tap idea as well. So sometimes it works with wire, and sometimes you just need to give it a little a little knock. And I think we might have made it. Let's just try putting our...
try and put a pin through it.
Yeah, let's try putting the pins through it. So we'll go back here. Alright, so there we are. We're back in the race here. So that's nice that I didn't plan on making that mistake, but just to let beginners know that you can kind of restart. And let's do that.
It also underlines the, place your components, tack them down,
Check
and
them.
test.
Yep.
Check for connectivity, check for alignment.
And you can also blow on stuff. If you're worried about overheating things, you have the cold air gun, which is basically you. Just blow on it. Alright, that's already had solder on it, so I don't have to hold it too long, hopefully. And there we are. Okay. So what I was doing while I was doing the corners, I had a finger on it. I was literally pressing it down, and the pressing down is what gives you, nice alignment. We're going to use that trick again when we do the others, but for now I'm just going to quickly race through. Getting the timing when you're doing a row of pins like this is really something that just takes practice, which is why I like getting these boards as separate components. It just gives you a chance to develop that skill. So first I'm holding the iron against the metal, and I sort of feed the solder into it, and then I just give it enough time for this.
And then lift the soldering iron with confidence.
Yeah, lift the soldering iron away from the pin to get the right shape. Okay, so I'm just going to continue this here. Alright, so that's the outer row of screw terminals, and again a little inspection just to make sure I didn't totally mess something up. At this point it would be really hard to fix a melting error, so you would just have to kind of go with it. But they all look pretty clean. The end one's got a little scuttly, but nothing that really stops them from functioning. You can kind of test all of that just by undoing them, and I usually undo all of these pins anyway. But if you do it at this stage, you can kind of tell if the screw terminal is still functional. And so, since we're going to be putting wires into these later, this is sort of your way of testing that you haven't monkeyed up the plastic too much while you did your soldering, is to just go through and loosen all the screws.
It's really good to build into the whole process, stop, check, verify.
Yeah.
It's like in carpentry, measure once, measure twice.
Yeah, this is one of those checks.
Yeah.
Not strictly necessary at this point, but it does give me an idea. No, the plastic's okay, so.
Well, it would be a shame to have 3 or several hours put into a device to discover later that one of them's not functional.
It happens. Then you end up with jumper wires all over the place to fix that one contact that isn't working, and yeah. Nothing's ever the end of the world, but you'd avoid it if you can.
Oh, just, it's like a lot of science and technology. Stop and look. Test.
It was really the end ones I was concerned about, but they all moved nice and smooth and they all look normal, so I'm going to call that a pass. Next ones are these. Now these are much, much smaller, so you have to be more careful not to melt this plastic on the other side. These are big, beefy honkers here, and so you can learn how to do the soldering properly with the first set, and then you carefully put these in.
So for alignment on those, is there orientation issues, or they're perfectly symmetrical?
They're
It's just
symmetrical.
They have to be vertical, though.
They have to be straight vertical, or we won't be able to get the Arduino on them later. And so what I usually do is very carefully as I can, put them down. And you have to kind of look under. You know, so when if you move from side to side, it's hard to catch this on camera here. Let me see if I can do it anyway. These things are very easy to get crooked. So if I just, you see all that wobble? So that wobble's quite nasty, and if you had one straight and one wobbled, you'd never be able to attach the Arduino later. So you got to make sure that they literally go on the board really perfectly straight. So I use.
Is there any way to tack them down with a bit of glue?
Not really. The easiest way to do it is to just do the same approach. Approach the corner. So I'm gonna have to get down here and look underneath the board, and I'm looking from the side here, and I'm just making sure before I do any soldering with my little screwdriver here that they are in fact really well straightened. And then I will do
the corner tacking.
The corner tacking just to make sure. And every time I do one of these, I'm actually going to.
These are slightly faster connections because there's less metal involved.
A lot less metal. So there's one corner tack down. I'll go and do this other one. And I'm holding the board with my finger to apply pressure so it stays straight on the table. And this other side's really crooked. I need to get under it, or I'll just turn it around.
The side you haven't tacked yet.
The side I haven't tacked yet, so I'm sort of poking it around with a screwdriver here. I'm looking at it. And I have my solder ready, and I'm just going to put a finger on the board to hold it in place. The first one is the tricky one. So, and you can apply some pressure with the iron itself too. But the trick is to just make sure those first joins are holding it in place. And you can go back and do them. If you make a kind of sloppy one, because this is a little tricky. There we are. That's looking alright. So I'll do the other opposite corner. And once you have the corners tacked down, then you can just sort of solder away.
Mm-hmm.
Alright, there's all four corners. A little bit of angle here, but not much. I think that's good. So I'm just going to do the rest here. Alrighty.
So that's good. What's notably good is that there's very little copper, and the shape of the Hershey kisses are nice and uniform, and they're not dimpled at the bottom. You know, sometimes that does happen. You just have to remelt it.
And the other thing to watch out for again is to just have a look, make sure you haven't accidentally melted, you know, your way through these. You have to be a lot faster on these inner rows than on those outer rows. Okay, so that's the terminals in place, and I usually stop at this point and I do a thorough cleaning of these guys. There's so much flux comes out because we're using quite a bit of solder. The rosin core that comes with, you know, your typical 60/40 tin lead leaves a huge amount of residue, and this stuff is very hydrophobic and it will corrode the contacts aggressively.
Well, it's a form of acid that actually takes a lot of the oils and the materials off of the metal and the plastics from manufacturing. Factories are not clean places.
Mm-hmm. Yeah.
So if you leave that hydrophobic acid on your metal contacts, it's hydrophilic. So it's absorbing water molecules from the air, and it's not uncommon to open up devices and find that your circuit boards have rusted away.
Yeah. So if you have a jewelry cleaner, you know, the ultrasonic jewelry cleaners do this pretty quick, but most people don't. And you know, you can, with a little bit of elbow grease, you can usually make a good job of it.
So The isopropyl alcohol is just from the drugstore. So your Walgreens, CVS, whatever your local is. The concentration doesn't really matter too much. We're using 91% isopropyl alcohol.
Actually,
if you can get the higher grade, it's a little bit better.
Yeah, I find the 91 does work better. The typical 70s-ish doesn't quite do the job as well. If I can get the 91, I would prefer it. But yeah, this is really just a cleaning stage, so.
But you do not need to buy laboratory grade.
No. This is just
domestic grade is just fine.
There are really nice solutions out there. Off the top of my head, I can't remember. There's stuff made just for this job, which does beautifully. But you know, again, it's a question of what have you got to hand.
Well, partly with the ethos of the project, this is material that can be typically purchased in most of the world.
Alright, so we've cleaned off all that excess flux before we go forward.
Close your alcohol so you don't get the fumes.
Alright, so now what we've done is we've basically done the manual version of the pre-made. And I like these because they're actually a little bit smaller. I don't know if you can see the size difference there. So this one fits nicer inside of the housing as well.
If you flip them over, it's good to mention, flip both of them over, it's good to mention that the traces that you can see between the two lines of contacts on the green one are actually present on the blue one as well. They just happen to be underneath the blue coating that's on top of them.
The blue one also has the ground plane covers the entire surface. You can't really pick that up, but there's copper all the way along the board. So if you're doing radio frequency stuff, that's actually better. That acts as a signal block. This one doesn't have any. There's no copper on the unused portions of the board. So if you had a radio frequency project, that would go straight through this board, whereas this would actually give you some shielding. So that's another thing to consider if you're choosing between these two.
Well, the flip side is if you need to drill an additional hole in the blue one, you also have to be conscious that you got to cut through it neatly and not delaminate and pull off all the copper and then affect your contacts.
Okay, so the next step involves paying attention to what's written on this board, and it's a little hard to see. But these boards were designed for nanos, and what we're using to build these loggers is a Pro Mini. So it doesn't occupy all of the pins, and some of the labels don't exactly line up exactly well. So you've got the digital side, which is has got TX, RX, reset, ground, and then D2 to D9. And if you get the alignment correct, if you spin your little nano board around, the digital side actually does line up. If you position the Arduino Pro Mini on the nano board with the TX and RX pins in the right place, those labels are in fact correct. It's the analog side of the board, that's the other side over here with A2 and A3, where the numbering starts to get muddled and it doesn't quite match.
A note of caution on that, we're currently in January 2019. You know, as time goes on, what's available on the market does and will change, and have had problems in the Earth 360 course at Northwestern where sometimes the components come in and they have different numbers of pins or they're labeled differently, and you do always persistently have to check your pins and your labels.
Yep. So what we're going to do is we're basically going to do that alignment check here. And there's the TX RX pin. And what I'm going to do is I'm going to mark the underside of the board, because now we want to add some components. We want to add a voltage divider to the bottom, but you need to not, lose track of where you are relative to this digital side. So I'm going to look at the TX RX. I'm going to flip it over, and I know that these are going to be ground side pins, and so I'm just going to basically give myself a reference marker here. These two pins are going to end up being joined together. That's the reset and the ground. That'll make sense in a moment. But basically, I like to label the grounds on the underside of the board so I don't actually do a transformation and start putting my voltage divider in the wrong place. As long as I have some sort of visual marker here, that lets me get all the other next steps without losing track of where I am. So over here, that's reset and ground, and I also usually mark the screw terminals as well. Again, these are just so that I have references so I don't do an inversion or a flip. And in fact, what we're going to end up with is another ground over here. So you can even mark this at this stage if you want to. This is on the analog side. But having those visual markers makes it easy for me to not make mistakes. So here's your RX and TX pin. This is a reset pin, which is going to be repurposed, and that's the ground pin on the digital side. This is the digital side of the board.
So, I mean, orientation really matters. Do you have a direction on the board that you typically think of as up?
No, I think of these boards in terms of front. The UART pins here on this one that's already been put in place, I think of that as the front of the board, and I think of that as the back of the board. This is the part of the board that's going to be populated with some of these other pins out here, but the UART board is really my reference. This is the UART communication pin. So I think of this as front and back, not sort of up and down. So digital side, UART pins. Alright, so the next step is to join some of these and add a voltage divider. Down here on the analog side, we have the raw battery inputs, and we want to run a voltage divider between these two inputs and then feed that to an analog pin so that we can monitor our battery voltage. So these two guys end up being...
Why do you have to put a voltage divider on the battery feed?
It has to be on the raw feed, which is higher voltage than the Arduino system. The Arduino runs at 3.3 volts, and so you have to break that voltage down. And you can use a voltage divider with a known ratio to take the usually 6-ish volts of your AA batteries that are powering the...
And bring it down into the range that the Arduino can actually measure.
That's right. The Arduino can only measure a voltage that's below the voltage of its rail. And that's true of pretty much all the microcontrollers.
So if you're working on a 5-volt Arduino board version, and your battery pack was providing 6 volts, you still would need a voltage divider of some sort.
Yeah, you'd still be too high to read with the analog inputs. So making a voltage divider is as simple as a couple of resistors, and I usually use very high value. This is a 3 meg resistor, and I got some 10 megs here. And the thing you run into...
So those are mega ohms, not kilo ohms.
That's right. You use really big resistors for your battery monitor because that way it doesn't bleed a lot of current when you're not using it, and that allows you to basically keep the battery monitor connected all the time. The amount of current that leaks through 10 meg resistors is so small it just doesn't affect your logger's operational life.
So usually when I'm buying the teaching kits or materials, there's sets of resistors that you can get that have a range of options. They typically do not include the mega ohm resistors, though.
Yeah, you might get a 1 meg ohm, but you're not going to get 3s and 10s. And part of the reason is that they're just a little more expensive, but they're also hard to work with. And I just want to talk for a moment about why they're hard to work with. It turns out that it's actually hard to measure these resistances accurately with a typical voltmeter. And that's because the voltmeter itself probably has somewhere around the range of about 20 megohms. And if you just use a sort of a typical cheapie, a pocket meter, and you make the mistake of trying to measure the resistance by holding it between two fingers, if you just try and measure a high value resistor like that, your body only has about 30 megohms of resistance. So you're creating a parallel circuit, and you will never get the right value measuring a resistor this way if it's at 10 megohms or above. And so you sort of have to invest in having at least one good voltmeter. This is an X-Tech 330. It's not really a good voltmeter, but it's $50 and it does the job reasonably well.
As opposed to a $6 voltmeter.
As opposed to, the ones we usually have. And the other thing to watch out for is you have to have alligator clips, because you can't hold it in your fingers. So let's pull out one of these 10 meg ohms and just measure it. And you'll see that it actually takes the meter a bit of time, because this is such a high resistance. It's not going to settle very quickly, and you have to be careful that you have a good grip, because at 10 meg ohms you can even mess up your reading just by virtue of not having enough enough pressure on your wire. And I'm actually having some trouble here, so I'm going to bend it a little bit. And it still sees nothing. Let's see here, come on. I made the mistake of taking this voltmeter into the field. Probably shouldn't have done that.
Yep, there we go.
Let's just see what we get.
That is 10.
That's surprisingly close. They usually aren't that good.
So that's been varying for a while.
Drifting, all right.
But
yeah.
The maximum is only 0.1 that it's varied to.
All right.
It's usually 0.05.
I think I'm just gonna try this again. Again, I'm worried that there's a bit of rust on my alligators, which is never good. I'm gonna actually change these. I think these clips are not clean enough to read meg ohms. Alright, so I'm going to try once again here. Let's just take one of these guys off. You need a good amount of pressure on the wire, because again, just the resistance, there we are. So now I have a good grip on that wire. Takes a little while to settle. Oh my gosh.
That is exceptional.
That never happens. Okay, so that was supposed to be a 10 meg, and it looks like it is actually a 10 meg. So that's rare. But just for my own reference, I'm gonna write this value on the bottom of the board, because I'm going to be making a divider with that resistor. So that's 9.9. That's remarkably close.
It's 10.
9.99 for our first resistor in our divider. You could probably note this in a notebook or anything. I just usually write it right on the board that I'm going to use the divider on. So that's our 10 meg resistor. And I'll pull off one of these threes, and there's no reason for this to be smaller. I like it as a visual reminder that prevents me from mixing up my resistors. If I use a 1/4 milliamp versus a rather watt versus 1/8 of a watt, this is the smaller resistor. I'm just going to set that down so I'm not shaking it.
You also want to read them fairly close to the resistor, because the ends were the pieces that were in those glued strips, which are used when there's automated assembly of devices. So those literally go through a machine and get pulled out, but there can be a little bit of glue left on the tips of the wires.
Whenever you have high resistance wires, there's all sorts of things that can come into play. So this is a 3.29. And I'm just going to write that on here, 3.28, 3.29. Okay, so 3.29. That's just so I have a record of this later. When I have to calculate the ratio that this divider is giving me so I can work on the battery voltage, I know the two values really well. And the next component I need is a capacitor. I'm going to make a little voltage divider with these two. Alright, these are just 104, I believe they are. Let's see here. My eyes are getting old. Yes, this is a 104 cap. So not very large. Its only purpose is to stabilize the output of the voltage divider, because the value of these resistors is so high that they don't allow enough current for the sample and hold capacitor inside the Arduino. The ADC requires you to be able to draw a little bit of current from your circuit, and with such high value resistors you can't really do that. So you have to add a little capacitor here, which helps deal with noise, but it also provides some electrons for the ADC. Again, this is only an issue most of the time with high value resistors like this. So I'll put the little 104 cap across the smaller 3.3 meg resistor, and then we wind up the 10 meg resistor on the one leg. And then we'll tin these legs so that we can add our bridge.
And these capacitors and these resistors, of course, are not directional.
Yeah, this is a ceramic cap. Again,
this type of capacitor is non-directional.
This type of capacitor. Many capacitors are. Yeah, and you just need the tiniest amount. Like I'm just using the head of a pin, and you want it to be almost invisible. If you can see the flux, you kind of have too much on there. So I've just tinned the ends of my voltage divider, and the idea is this is just going to sit in the center here at the bottom of the board, and what we want is the ends of this voltage divider to be the raw battery voltage and the ground. So these two here, if I flip it over, it's quite hard to see, but this says V in and ground on this side. This is the analog side of the board. There's the digital side that I was talking about that matches, and this is the analog side where the pins do not match. And these first two here are the power in. And so it's a little bit tricky. I'm going to have to do some bending here just to get these things to come in and align properly. And I like to use thin needle nose pliers for this kind of job. It's a little bit tricky. If you don't have thin ones, these tend to do a nice job, because I want a little bit of separation between the capacitor and that pin. I don't want there to be an accidental contact there.
You don't want to puncture the capacitor with the pin.
Yeah, well, you just don't want any sort of place where there's going to be an extra contact that's not necessary. But you can see there's not a whole lot of space there. Not a whole lot of space there for mistakes at this point. So we want to be able to just sort of curl that around the pin. In fact, usually what I do is I even just hold it with my thumb, the same way I'm holding it now, and I'll bring the solder in. Now all of the points that we're soldering here already have solder on them. So all I'm doing is bringing the wet tip to join them together, but it's just melting things that are already covered with solder. So I should be able to make that join without too much difficulty. So there's the first one, and that's the ground side. The smaller resistor in the divider goes to the ground leg, and again that's the ground leg as labeled here. And I'm just going to bend the other one around. I don't want these to come in contact. Remember, this is the raw voltage input from your battery, so you want to have, a little bit of room here. You want these wires to parallel each other but not actually come in contact. We're going to be coating them with conformal later on, so they will become protected from accidental breaks.
So right now you're putting a bead of solder on the tip of your soldering iron.
Yep.
And then bringing it into the contact.
Bringing it in, burning my fingers a little bit here.
Well, that's actually good. It means that you're not going to overheat the component.
Yeah, these little resistors, it's easy to mess them up. I'm actually hurting my finger a little more than I'd like, so maybe we'll put this in a vise for this job. And once you have something in a vise, you can come in with your tweezers and hold it in position. And the tweezers won't complain, but again you have that risk of hurting your component as well. Okay, so I'm just trying to hold the wire down. What I want is for this wire not to jump up once the solder's removed, so I'm just going to position it, hold that down. And you want to be careful you haven't created a solder bridge. This is the trickiest part, I think, of this whole build, is not joining those two while you're doing this little bit of soldering. You do get a sense of it after you've had a bit of practice, but it's real easy to make an accidental join. Once I have those in place, and this is, these two wires are far from each other, there's no worry, I can
capacitor is away from the pin.
Capacitor's got lots of room, it's not away from the pin. There's no join here, and these wires have lots of room to to be where they want to be. The last connection is going to go up here. Now this one's going to become a ground, but just below it we're going to have an extension of the analog pins. This particular Pro Mini clone has A7, A6, and ground, and we're going to be carrying those up to these unused pins here. And so we're going to actually use A6, which will go up to this pin. Later on it will be connected here, and the output of the voltage divider is going to be brought to that A6 pin.
So we're going to the second pin.
Second from the top.
Okay. And that's a stiff wire now because you've twisted 3 wires together.
Yep.
And you've also tinned them with solder.
And I've tinned them with solder. So again, it's a little tricky to do the soldering, but not too hard. And you can hold it in place. As I gave the wire a little bend. I'm doing my best to make sure that I'm not accidentally grounding this. I'm trying not to make a bridge here between those two, but you should be able to just remelt that point, let it cool.
With this kind of solder contact though, it's really important that the wire and solder do not move while it is cooling, because that's a really good way to get a failure.
Alright, that was our voltmeter just timing out there. A little beep. Alright, so now we have a 10 meg ohm resistor going to the voltage in pin from our battery bank, and we've got a 3.3 meg resistor, or in fact 3.29 because we've recorded the value here, with a 104 capacitor across it, and then the output from this voltage divider goes up to what will be the A6 pin.
Perfect.
So that's one of the things we want to do on the bottom of the board. Since we have it in place here, the other thing that I want to do is reposition, or rather bridge, these 2 pins here and these 2 pins here. What we're going to be doing is not connecting the reset pins so that we can have more ground connections and more power rail connections later on in the build. And so I'm going to take a resistor, and this can be any resistor, it doesn't matter what the value is, although I would use a common value because the high value resistors like the 10 meg are a little hard to get a hold of. But we're just going to take a wire and we're going to just create a bridge over these 2 connections, and we're going to get another wire, we're going to bridge this, and we're going to carry it up and over to this far corner. Again, you can never have too many grounds or too many power rail access points in a data logger. You almost always need to draw another set of those every time you connect a sensor. It's just a good idea to have at least 2 or 3. So whenever I'm
so that's a bit of flux on the wire.
Yeah, a little bit of flux. I'm just using this as a wire. I think this is a 4.7K. I don't actually care what the value of the resistor is. It's just a cheap, convenient source of wire for this kind of thing. And if I get a little blob, I'll just cut it off. I want the wire to be fairly clean. And I'll twist a nice little round end on it. This is the other thing that you can do with these tiny needle nose pliers that's a little hard to do otherwise, is you can put a little hook on there, and I'm going to use the outside edge because these are slightly bigger contacts, they're easier to work with. And so this is 1, 2, 3. I'm joining 3 and 4 on this side. Okay, and I just had to melt that. I didn't have to do very much to it. And now I'm just going to wind it around the other pin that I'm trying to bridge. Okay, so there's our repurposing of the reset pin, which we won't be connecting, so that we can get another ground. Okay, and that's a bit grimy there, but I'm just going to trim away the excess. All we needed was that. Okay, so reset and ground are now both connected to ground, and we'll have to make sure we're aware of that when we pin our Arduino board later. Now I'm going to do the same trick over here with these 2 pins. This is the reset pin and what will be the 3.3 volt rail, and I'm going to join both of these guys with a wire, and then I'm going to carry it up and over and turn turn this pin over here into another access point for the rail voltage, and that'll end up going to our RTC later.
So but first you're going to use the resistor wire for joining those two pins.
No, in this case, because I want to carry it up, I'm actually going to strip a wire and use the end of a wire as my bridge. So I'm going to tin that. So instead of using a resistor, I'm going to use this here. I'm still going to do the same trick. Makes it easier if you bend a little hook in one end. So on this side, on the analog side of the board, this is the 3.3 volt rail.
Do you have the insulation cut back far enough? Like, how do you know if it's far enough back to?
Well, you can see it. You can see those two pins that I want to join are part of the exposed wire, so that just melts that into place.
But you don't want to have too much insulation off that wire because then you risk a contact with the next
That's
pin
right.
up.
You can see the insulation starts at the next pin that I'm not trying to join, so that it's unlikely to give us an accidental connection there.
Do you ever pull on your connections to test them mechanically before?
Yeah, always is the answer there. You always want to make sure you don't have a cold joint. So I'm just going to run this wire between this set of pins and then over to this top corner. And this is the next connection that we're going to be making here for access to the digital side. The digital side doesn't have a rail connector, so I'm just going to put this on the very end. And we sort of run it up.
So you've sized the wire.
Yeah, the wire's long enough to run in this channel here and then across, and I usually leave about 5 millimeters longer than I want in my connection wire.
Snip it with the side snips, not the wire strippers.
No, the wire strippers are only for stripping. Alright, so let me just pull that off. It's always harder with red. Whatever they put in the plasticizers for the red silicon wire, it does not want to cut properly. I don't know why it's only that color. I'm sure it affects the chemistry in other ways. The rule of soldering is always, if you can, make sure everything you want to join is already tinned before you bring it together. So we know this pin is tinned and now the wire is tinned. And I'll give it a little bit of a loop. Hold it in place over the pin. Again, this is a silicon wrap wire, so the insulation is not in danger of melting, and it also protects my finger a bit when I do this trick. But if
it's also very flexible.
Yeah.
Very soft.
Okay, it's a little hard to get a nice Hershey's Kiss on these joints because there's so much wire there now. The key thing is not accidentally bridging. We're a little too close for comfort, so I'm going to pull that away. That's a bit of a glob, but it's not in contact with the next pin. That's all I'm really worried about here. Okay, so what I've done is I've first joined these two. That's the reset pin and the VCC pin, and now I'm running it up and over just to get another power point up here for the rail voltage. So that is essentially the bottom of the SD board done, and when I reach this point it's time for some conformal coating. We'll be putting some double-sided tape on here later, and before I do the conformal coating, which is this MG Chemicals, if you've made a bit of a mess with your solder, you'll be able to see it. Like we cleaned this board up pretty well, but if you see sort of shiny patterns down there, take a moment and give it another cleaning. It's not needed in this case, but if you've had to model around, you might end up with more more flux that needs cleaning. I did a fairly clean job, so it doesn't really need it. But you know, you can give it another wash over. Be careful that the alcohol will take off your markers as well. So anything that you've noted down there, like our value, we've got a 9.99 meg and a 3.29. Those values are actually important for us later. So you don't want to accidentally erase them when you do, you know, your last cleanup on the board. One of the nice things about using the 90% alcohol is if you have a heat shrink gun, it'll just evaporate in no time. So I can just give this a little gentle heating to make sure there's none of that alcohol left, because I don't want to go to the next stage, which is conformal coating, while there's still moisture on the board. So you got to make sure that it's nice and dry, and you know, just a few moments with a heat gun will quickly take care of the isopropyl alcohol. And then we will give it some conformal coating. Now this is nasty stuff. This is definitely fume hood only for the purpose of this video. We'll just do it here, but I normally do this outside. And it gets all over the place, and it's kind of got the consistency of nail polish. In fact, some people use nail polish. If you can't get your hands on this conformal coating from MG Chemicals, nail polish actually works quite well to do protective layer. And the idea here is I'm just trying to make sure no moisture gets in on these contacts, because if it does, you will end up later on with rust destroying your circuits.
You're aiming for a complete seal on all soldered contacts. In this case, it actually also serves as a bit of a glue to keep the wire in its location, and then also the voltage divider with capacitor bridge.
Yeah,
will also get glued down to the board.
It's providing a nice accidental contact protection here as well. When this stuff dries, of course it doesn't conduct, so we didn't put heat shrink down here, which you can do for a little more protection, but once you've got it coated with conformal, it's pretty safe from accidental contacts. What you don't want to do is put so much on here that it runs around and ruins the electrical contact on the other side. It's one of those things you just practice. Just enough is what you're trying to aim for here.
The other thing too with conformal coating is it's a one-way trip. Once you put this on, you're no longer planning on soldering or connecting anything to this side of the board.
Yeah, kinda. You can fudge it. You can burn it off. If you didn't put too much on, you can cook it off later if you have to do repairs. So I've had to do repairs through this stuff, and it's actually not that bad. I haven't had to re-solder through nail polish. That might be worse for you, but this conformal coating I use, the MG Chemicals, what is it now, 422B, really nasty fumes. I mean,
in a classroom setting, before putting the conformal coating on is when, you know, I was, as the instructor, would do the review of the work and give you the thumbs up.
Yeah, thumbs up.
You're good to go.
Before you do the conformal. And then it needs to sit for 15-20 minutes. You can't really do anything to those surfaces until then. But that essentially is the first component of the logger. So ready for the next stage, ready for assembly. We're going to be putting some double-sided tape along the edges, but that can't happen until the conformal coating is done. So at this point, the screw terminal component of the build is ready for the assembly stage. We'll move on to the next piece.